I think we can start with the second speaker of the this afternoon session, which is Emily Roth, and she will talk about magnitude homology and iterated enrichment. Thank you. You can go.
Thank you. Yeah, thank you to all the organizers, and in particular to the scientific committee for the opportunity to speak. And thank you to anybody who's up at an unsociable hour to be with us Europeans. So my name is Emily. I'm a PhD student at the University of Edinburgh, where I'm working with Tom Leinster. And broadly speaking, my research has to do with numerical and algebraic invariants of enriched categories, which generalize or categorify cardinality of sets. And typically, so if you're familiar with Tom's work over the last decade or so, you're probably familiar with this idea and the fact that typically these invariants turn out to be of particular interest when they're interpreted from metric spaces as categories enriched in the positive half line. But the story that I want to tell today is not primarily about metric spaces per se. I want to talk about a homology theory known as magnitude homology, and I want to talk about it in the specific context of iterated enrichment, which is to say that I want to talk about the magnitude homology of categories that are enriched in some category of enriched categories. So if that sounds maybe a little bit arcane, let's start by reviewing some examples that this ought to encompass and why you might be interested in them. So first of all, obviously a two category is enriched in the category of set categories. It has a second order enrichment in the category of sets. A strict n category is a category with an n-fold enrichment in sets. So this gives us one class of examples. And in particular, any locally posettal two category can be seen as falling into this class, but equally we could choose to regard it as an example of metric enrichment in the category of metric spaces, where by metric space I mean Lovir metric space category enriched in the positive half line. And I'm going to refer to metrically enriched categories as locally metric categories. So today, I'm mainly going to be talking about the homology of two categories and of locally metric categories. And I decided to focus on metric enrichment in this talk at the expense of two groups and these things I'm calling suspensions, because among other things, they give us one way of getting a handle on what Alyoush and Simpson have called approximate categorical structures, Tolan and Wang have called metagories, and these are essentially met-enriched graphs, but it's maybe more instructive to think of them as category-like structures in which it makes sense to talk about some morphism being epsilon close to being the composite of two others. And structures like these strike me as interesting, perhaps from the point of view of applications, so, say detecting or identifying categorical structure in real-world systems. And some of the natural questions that you might ask about the relationship between approximate categorical structures and metric enrichment seem to have a sort of homological flavor. So for instance, can homological tools be used to help us quantify the failure of an approximate categorical structure to be an honest category? So I'm not really going to talk very much more about that in this talk, but if you've been thinking about those things, I'd be interested to chat about it later. Okay, so here's the plan. Sorry, there we go. So first, I'm going to give you a kind of whistle-stop introduction to magnitude homology, and that's part one. Then in parts 2 and 3, we've got the new stuff. So I'm going to propose and justify a definition of magnitude homology for categories with an iterated enrichment, and then we'll see how it plays out in the locally metric case. Okay, so the theory in this first section is largely due to Tom Leinster and various of his collaborators, particularly Mike Schulman, Simon Willerton, and Richard Hepworth. So to motivate magnitude homology, first I should briefly explain something about magnitude itself. So magnitude is a machine that takes a notion of size for objects of some monoidal category V and returns a notion of size for categories enriched in V. Of course, the notion of size that you start with has to be a good enough one. So in particular, it should be isomorphism invariant, valued in some ring, and multiplicative with respect to the monoidal product in V. And then the notion of size that you get out for V categories is going to be equally good. It'll be equivalence invariant, valued in that same ring, and multiplicative with respect to the tensor product of V categories induced by that in V. So to give you the idea, here are the key examples. So in the original motivating example, you say that the size of a set is its cardinality. Then magnitude tells us that the size of a finite category is a rational valued generalization of topological Euler characteristic. So for instance, the magnitude of a groupoid is its groupoid cardinality. When it comes to enrichment in the positive half line, magnitude tells us that the size of a metric space is most naturally interpreted not as a number, but as a function. And in the case of a finite metric space, this function can be thought of as recording the effective number of points in the space as the metric is scaled up and down, or if you like, the effective Euler characteristic of the space at different scales. And a magnitude function can be defined for many infinite compact metric spaces. And in that context, it turns out, thanks to hard work by these analysts and others, it turns out that the magnitude function detects a whole lot of more kind of obviously geometric size-like quantities, including Euler characteristic again, but also volume, surface area, things to do with curvature. So in each of these examples, magnitude has an important relationship with Euler characteristic. In fact, it specializes to Euler characteristic in at least 2 or 3 different ways. And there are good reasons to be interested in Euler characteristic in itself, but on the other hand, it's like an important part of the origin story of category theory that Euler characteristic was like this one-dimensional piece of information destined to be unfolded into a multi-dimensional spectrum of data, the singular homology of the space, which isn't just more informative, but also easier to reason about because it's functorial. So naturally, one wants to attempt the same sort of thing with magnitude, and that's what I'm going to tell you about in the next few slides. So, just as magnitude allows us to lift a notion of size for objects in V to one for V categories, magnitude homology is going to allow us to lift a categorification of size to a categorification of magnitude. So in order to tell you how to categorify magnitude, I first need to tell you what it means to categorify the size. I need to tell you what it means to be a size functor. Okay, so for the theory of magnitude homology to work, we need to impose a restriction on the enriching category V. So we need to ask that V is semi-Cartesian, meaning that its unit object is terminal. And this is not required for magnitude, just for magnitude homology. And it's sort of technical. It's to be hoped that this can be removed because it's rather restrictive. But for the moment, we require that V is semi-Cartesian. So suppose V is a semi-Cartesian monoidal category equipped with a size valued in some ring R. And suppose we've got a closed symmetric monoidal category, abelian category A, equipped with a rank function also valued in R. And by rank, I just mean something which shares the good properties of the torsion-free rank of abelian groups. Okay, so suppose we can find a strong symmetric monoidal functor from V into A with the property that the size factors through this functor sigma via the rank. In that case, we're going to say that sigma is a size functor, and we're going to say it categorifies the size hash. Okay. So now I need to tell you how to lift the size functor to a magnitude functor on VCAT, and this is going to be valued in the category of n-graded objects in A. Let's see how it works. Okay, so here's the idea. Magnitude homology is going to be constructed as a composite of 3 functors. So the second category is obviously the simplicial objects in A. This is chain complexes in A. H is homology of chain complex. C is the unnormalized chain complex of a simplicial object. So really all I need to tell you about is what this first functor here is doing in B sigma. And this is what we call the magnitude nerve. So I've given you the construction of the magnitude nerve in degree n. The face maps here are really the only thing they can be. So these internal face maps are induced by composition in X, and the extremal ones, delta naught and delta n, are induced by terminal maps in V using the fact that V is semi-Cartesian. and the degeneracies are induced by inserting identities on the objects of X. So maybe the quickest way to understand this is just to see that if V is set and sigma is the free abelian group functor, then the magnitude nerve is just the simplicial abelian group you get by applying sigma to the ordinary categorical nerve. Okay, so the magnitude complex of X is the unnormalized chain complex associated with the magnitude nerve, and the magnitude homology of the V category X is defined to be the homology of its magnitude chain complex. So in particular, sorry, my slides jumped. In particular, if you're, for an ordinary category, small category X, the magnitude homology is just returning the homology of the classifying space, the geometric realization of its nerve. And yeah, this works. So the main theorem of Tom's paper with Mike Schulman says that for a finite enough V category X, the Euler characteristic of its magnitude homology, which is to say this alternating sum of ranks, is equal to the magnitude of X. So we can ask, well, what does this give us? And thus far, most of the investigation has been in the context of metric spaces, where it's been shown that magnitude homology is recording a bunch of interesting geometric data, the cardinality, but also some quite subtle information about convexity of the space. And it's counting holes in the space, but not just holes, also in a relevant sense, their sizes. And it says something about the uniqueness of geodesics in the space. Okay, so in the case of ordinary small categories, magnitude homology is giving us something classical, it's giving us the homology of the classifying space. And in the case of metric spaces, it's giving us something novel and interesting. It's a genuinely metric homology theory for metric spaces. So it seems like a reasonable superstition that a magnitude homology theory for locally metric categories, which have both ordinary categorical and metric structure, should give us something worth studying. But how should we define it? So according to the recipe that I've just given you, we need to start with a size on the enriching category, category of metric spaces. And what is the size of a metric space? Well, how about magnitude itself? So I described magnitude as a machine that takes a notion of size for objects of V and gives you a notion of size for V categories. And the idea now is that by running that machinery a second time using magnitude as our notion of size for V categories should give us a good notion of size for categories enriched in VCAT. And here I'm writing 2 VCAT for the category of VCAT categories. So super simple idea, and it's mentioned in Tom's first paper on magnitude. And a few years later, Kohei Tanaka wrote a paper using this idea to define the Euler characteristic or magnitude of a bicategory. But what I want to talk about is what should go in this empty corner here. So is there a way to categorify the iterated magnitude of a VCAT category? And since in the top left we have magnitude with respect to magnitude, a reasonable first guess would be that in the top right we should have magnitude homology with respect to the size functor magnitude homology. But for that to make sense, magnitude homology would have to be strong symmetric monoidal, and in general it's not. So we have to do something slightly different. And the key is that the magnitude nerve is strong symmetric monoidal with respect to the tensor product of V categories and the pointwise tensor product of simplicial objects. And proof is just a straightforward check of a bunch of coherence diagrams. And as a corollary, we get a Kuna theorem, a general Kuna theorem for magnitude homology, which recovers Kuna theorems previously proved for graphs and for metric spaces by Hepworth and Willerton and Bottinelli and Kaiser. But I really just include that for completeness, because the point is that knowing that MV sigma is strong symmetric monoidal means that we can plug it in as our size functor. So MV sigma is valued in a category of simplicial objects. So the magnitude nerve with respect to MV sigma is going to be a simplicial object in simplicial objects, which is to say a bisimplicial object. And in order to talk about its homotopy or the homology of an associated chain complex, we really want to recover an ordinary simplicial object in A. So we do the simplest thing we can do, we take the diagonal. And then the iterated magnitude homology of a VCAT category is defined to be the homology of the associated chain complex. if we want, we can continue iterating to define a magnitude homology for categories with a higher order enrichment. So in particular, this gives us magnitude homology for n categories for any value of n. But today I'm just going to be talking about n equal to 2. So I said that the magnitude homology of the ordinary small category is the homology of its classifying space. And one can define a classifying space for a 2 category as well. In fact, there's in principle more than one sensible way to construct a classifying space for 2 categories. I'm just going to briefly talk about that. So yeah, on the left here, this approach is due to Siegel. So Siegel said, take your 2 category X, so its home objects are categories, and by replacing each home category with its classifying space, we get a topologically enriched category. The nerve of that topologically enriched category is naturally a simplicial topological space, and we can geometrically realize it to get a single topological space, which can reasonably be called the classifying space of the 2 category X. But there is another sensible way of approaching this, which is to first build what's known as the Duskin or street or geometric nerve of the 2 category. And this is a simplicial set whose m simplices are normal lax 2 functors from the linear order on n+1 objects, regardless of bicategory, into X. Normal meaning that they preserve identities strictly. And this nerve extends the ordinary nerve construction on small categories. So it also seems sensible to talk about this thing as being the classifying space of X. And like, to me, it's far from obvious that these 2 constructions should have much to do with each other, but fortunately, it turns out that they do. So Bullejos and Thegara proved back in 2003 that there is a natural homotopy equivalence between Siegel's classifying space and the realization of the Duskin nerve. And so we can refer to the classifying space of a 2 category without too much anxiety. And that allows me to state this first lemma about iterated magnitude homology, which says that the magnitude homology of a 2 category is the homology of its classifying space. And I mentioned that Tanaka has studied the magnitude of bicategories, and the main theorem in Tanaka's paper says that the Euler characteristic, the magnitude of a bicategory is equal to the Euler characteristic of its classifying space in the Duskin sense. And so combining Tanaka's theorem with his lemma, we can immediately conclude that the magnitude homology of 2 categories does categorify its iterated magnitude. And proving the same thing for locally metric categories is more involved because we don't have a theorem like Tanaka's to rely on, but it does work. And the proof uses general facts about spectral sequences and Euler characteristic. Okay, so iterated magnitude homology does succeed in categorifying iterated magnitude in each of the 2 main cases that we're interested in. And we've seen, at least in abstract terms, what the magnitude homology of a bicategory or 2 category sees. And in the final few slides, I just want to tell you what I know so far about the iterated magnitude homology of locally metric categories. So the theory of magnitude for metric spaces strongly motivates a particular choice of size functor on the category R+, which is valued not in abelian groups, but in a category of R+ graded abelian groups. So an object here is just a family of abelian groups indexed by the positive reals. We're forgetting about the ordering. And so the iterated magnitude nerve of a locally metric category is going to be a simplicial object in AB R+, or equivalently an R+ graded simplicial abelian group. So to spell out what the nerve is, I need to tell you what it looks like in gradings n, and for every natural number n and positive real number L. So here we go. So in degrees n and L, it's generated by these sort of string of beads diagrams of arrows and X, sort of arrays of arrows that compose in this manner, and such that the lengths of each of these paths, so the sum of distances in each of these columns, sums exactly to L. And I'm just showing you this to give a sense of the kind of data that we're dealing with. I'm not going to ask you to think about it, so I'm not giving you all the details. What I want to do is just to state a theorem about describing parts of the homology of the associated complex. But in order to state that, I've got to introduce just a little bit more terminology. So I need to tell you what a gap is. So a gap of width L in a locally metric category is going to be an equivalence class of irreducible pairs of parallel arrows in X separated by a distance of L, where L is a positive number. So first I need to tell you what I mean by irreducible, and then I'll explain what this equivalence relation is. Okay, here are some ways that a pair of arrows might be reducible. So perhaps, so we've got f and g from x to y, and perhaps it's the case that there exists some h from y to z, such that when we compose it with f and g, it reduces the distance between them. So the distance from h after f to h after g is strictly less than the distance from f to g. So in that case, we're going to say that h tightens f and g from the right, and equally if there's some k that composes with f and g from the left, to reduce the distance between them, we'll say that k tightens f and g from the left. And if there is no arrow in x that can tighten f and g from the right or the left, we'll call that pair tight. Here's another way that a pair might be reducible. So perhaps there's another arrow, say h from x to y, which is strictly between f and g, in the sense that the distance from f to h plus the distance from h to g is equal to the distance from f to g, but the distance from f to h is strictly less than that from f to g. In that case, we'll say that f and g can be bridged. And if f and g can't be bridged, we'll call that pair adjacent. One more way that a pair might be reducible is perhaps f and g actually factor exactly into two pairs, the sum of the distances between which is equal to L, but each of which is strictly smaller. And in that case, we'll say that f and g split. And if f and g don't split, we'll call them simple. Okay, so an irreducible pair is a pair of parallel arrows which is tight and adjacent and simple. And we can define an equivalence relation on the set of tight, simple, adjacent pairs generated by these two relations, which are saying that two pairs are equivalent if one can be obtained from the other by composing with a third arrow that doesn't tighten them. Okay, so now I can state the theorem. All right. Okay, so theorem describes the iterated magnitude homology of a locally metric category with separated Hom spaces. So for example, if the Hom spaces are genuine metric spaces. So in grading 0, it turns out that iterated magnitude homology completely recovers the ordinary categorical homology of the underlying ordinary category. And I wouldn't necessarily have expected that because it's constructed from the magnitude nerve of a metric space, which has quite a different flavor. But it turns out that iterated magnitude homology knows everything there is to know homologically about the ordinary categorical structure of X. And in positive gradings, the first two homology groups vanish, which reflects, I think, that in a locally metric category, all of the non-trivial metric action is happening in categorical dimensions 2 and above. And indeed, for its MH2 is starting to pick up information about the metric structure. It's freely generated by the gaps of width L in X. And I think the fact that MH2 is counting gaps along with their widths is closely related to the fact that magnitude homology for metric spaces counts holes along with their sizes. And in this locally metric context where we have composition going on, and so there's a potential for tightening and splitting, there's a bit more nuance to what a hole is, and the homology theory is picking up on that, which I think is quite nice. So, okay, finishing up, to summarize, it's iterated magnitude homology is a homology theory for categories with a second or higher order enrichment, which categorifies their iterated magnitude. It specializes in the case of two categories to the homology of their classifying space. And in the case of locally metric categories, it combines, as you might hope, features of the ordinary categorical homology of categories and the magnitude homology of metric spaces. And I'm just going to leave a few questions on this slide. but I'm finished now.
Okay, thank you very much, the speaker. And so there's some time for questions. So if any, please, I'm checking on the Zoom and in the room. Any question or comments? Check again. So if no question, let me thank the speaker again. Thank you, Emily.
Thank you.